Good day to you all. Shall we pray? Oh Lord, thank you this day. You bless you for this class. We ask you grant us grace to obtain. Your name be highly exalted and glorified. In Jesus' name we pray. Amen. Alright, like previous classes, this is also the next topic. Normal stress, chapter 2, normal stress due to axial load. From the PDF I uploaded, you see there and you follow alongside the video. Load. Any external force that is acting on a rigid body are called load. Load is any external force that are acting on a rigid body, and we have types of load, which we have the first part. We have the axial load. We'll be considering the axial load now. We have the shear load. We have this is shear force, like that. We have the bending moment, and we have the torsion. So we'll be considering axial load majorly now. And axial loads are load that are applied alongside. They are load that are applied alongside the longitudinal parts. Example like this. It can be compression or it can be expansion. So if I drag this man, let's say the force acting on, let's say the fan in your house is acting downward, that is gravitational force, and that fan there, if it is being dragged, or let's say you drag the boat edges. So this is a fan sample. You have 3 fans fin there, and like this, and you drag these 3, you drag them like this with a force P1, P2, P3, P1, P2, P3. This kind of load is called axial load because they are acting alongside the longitudinal part. And this kind of load is not compression. You're not compressing it, and that is, you can call it tensile. You can call it let's say tension. You get what I'm saying? So in a nutshell, when I apply force, or let's say these are loads that along their longitudinal or centroidal structure of manner in such a way that they tend to increase their length of members. They tend to increase after dragging or after stretching them. It's said to be in tension. So this is an axial load. Axial load that is acting alongside the longitudinal part is tension. The longitudinal part is tension. Now, if this load also is being compressed, that is, it tends to shorten the length of the member. Let's say another force P also, or not in this side, like this. So it tends to shorten. So I compress this together. The size will be somehow like this, be somehow up, and it will somehow slow, and to go like this. So this is the bending moment. Though we're still going to consider that is after it's stretched, and this will go up. That means it can also be this size. But if it's expansion, it will somehow be like this. Somehow be like this. It will expand, it will stretch and shorten like that, and this will shorten. So I'm saying this is for tension, and this one is for expansion. This one is for compression. So you have 2 types of axial load, which are tension. When load is in tension, that is, it tends to length, it tends to increase. And when it is in compression, it tends to shorten or decrease. So types of axial load so far. Axial load are loads that are applied along the longitudinal or centroidal axis of a structural manner, and if the action of the load is to increase the length of the member is said to be in tension. And if it is applied, or you can call the load that this force is called tensile load. This is called applied load rather. This load is called applied load. Now if it is to shorten the member, this is also called compressive load, or you call the kind of force there, or it's called compression. Okay, so also considering shear load, which is number 2, shear load acts perpendicularly to the axis of a structural member. Example, for let's say we have a cantilever. We have types such as cantilever, and it's like this. It is a kind of load whereby the force acting on it, or the weight acting on it, is at the edge. It can be like this, or it can be like this. So this is a such one whereby let's say this is a beam. This diagram is a beam which is fixed or built at one end of a free end, and something about this is that it is fixed at the edge of a particular other end. So it is fixed like this. So let's say this is imbibed to the wall. Now this is a cantilever. This cantilever. And also we talk about let me say the second part is for simply supported type. Simply supported is such one whereby you have the load like this, and you have different kind of force acting, probably at the centroidal or at the center, and you can have two supports that are supporting. This can be a roller. A roller is like this, or a pin. A pin is like this. These are used, the practical application of these things are used in tractors to create borehole, where company, in terms of digging, in terms of making this well, or in terms of digging deep for different kind of minerals. Okay, and we now have the tensile. We have the tensile stress, or the total stress rather. We have total stress is equals to the total internal force within a single member. So we can now say that this is total internal force within the single member. That is P1 plus P2 plus P3 plus Pn. So we can now say that whereby this P are not load, they are just stress. So we can now say that okay, that this stress denoted as, or sigma, this is stress, is equal to your applied load over the area. So you can say this is stress intensity, and this is the applied load over the area. Or you can say area of cross section of the cross section. So, and also we have the normal stress. So let's say consider a bar, 2 bar. A bar in tension will be like this. The bar will expand, so it will have this kind of force. To have this kind of dragging, is like you are dragging it, you are dragging like this to expand. But compression will be like this. A bar in compression will be like this. Someone will be pressed inward. Also, strain is the next part. Strain can also known as this sign, this notation. Strain is also defined as a change in length over the original length per unit length, change in length per unit length. And there's what we have stress to strain relationship. Stress to strain relationship. Stress to strain relationship is diagrammatically represented as this, and you can have it as when you drag When you drag a rubber, let's say nylon, polythene, and you drag it, you find out that it will sustain that drag. Let's say a rubber, it sustain that drag continuously, and this graph can be stress to strain. So when you drag a particular member, you drag it will sustain that particular drag, and after a while it would come to a point A, come down to point B, come down to point C, and come down to point D, and then for break finally. So we have point D, point A, point B, and point C. This point, and this point, and also this point. So this phenomenon is called elasticity, and elasticity is the defined as a ratio of stress to strain. And elasticity is also a phenomenon, or it's an elongation whereby a member is being dragged and is being stretched, so it expands. So this phenomenon is elasticity. So now, considering this diagram, a certain material at point A here, when it gets to point A, it will sustain this point from this point 0 here to point A, and when it gets to point A in this point there, this limit is called limit of proportionality. Limit of proportionality. And also this stress to strain curve, it does not remain linear. It's not linear, like you can see, it's not linear. And now when it is being stressed beyond B, it is known as elastic limit. This is the limit it can sustain before the second process or the third process. And when you now stretch it beyond B, and in this phenomenon is called elasticity, but when you stretch it beyond B, then there are certain amount of strain that are permanent that will start happening. So when it is stretched up to C, beyond C, it will start straining, and it will somehow extend, that it can retain that elastic property. And when it gets to D, is called yield stress. This yield stress is a point whereby the material cannot come back to its initial state. It has reached the maximum, and this D is known as the ultimate stress. So this point here to here, ultimate stress, this is yield stress rather, and this point D like this is called ultimate stress. Ultimate stress. So at point A, we call it limit of proportionality. The material can still go back to the original state, and that is elasticity. When you get to B, that is elastic limit. Now this elastic limit can still go back, and that is elasticity. But when you get to point C, this point C is yield stress, and this point like this is yield stress to here. This point like from here to here is yield stress. This yield stress, when it gets here, it cannot, but it will have the yield. The material would not be able to back. Now when you get to D, this is ultimate stress. It's already fragile, it has already broken like that, and therefore we now have the ultimate stress formula. Ultimate stress to be equal to your maximum load over original length multiplied by the sectional area. So in other words, we can have the ultimate stress to also be denoted as the ultimate stress as this. So ultimate stress like U like this equals to the maximum load P max over the original length times this. So now this leads us to Hooke's law. Hooke's law. So Hooke's law states that for material subjected to simple tension or compression with elastic limit, the stress is proportional to the strain. So now Young modulus can now be defined. This is E. I state Hooke's law now that I just stated down. Hooke's law states that for material subjected to simple tension or compression within elastic limits, the stress is proportional to the strain, like you see here. And this is just a constant. So it is the stress is proportional to the strain, whereby E is constant. This proportionality, this proportionality of the constant or constant proportionality. So this guy here is now the Young modulus. Okay, so this constant E is now the Young modulus of elasticity and is denoted by E. Now this Young modulus, it's very important you know all this law. This Young modulus E is now defined as a simple tensile or compressive stress within elastic limits required to produce unit strain. I come again. The Young modulus may be defined as a simple tensile or compressive stress within elastic limits required to produce unit strain, and the SI unit of E is kilogram per centimeter square. Otherwise, you are given a question, you will do it to change this square, this centimeter to meter. Okay. So we've learned from Hooke's law that E is directly proportional to is equal to stress over strain, and you know from the basis that stress is equals to force over area. But for this elongation, we have it that stress is equal to load over area. Okay, and also we can find out that our strain here is equal to change in length over the original length, and where our Young modulus is equals to PL over A times the change in length, and that's also PL over AA. So we have or change in length is equals to your PL over AA. So your change in length is elongation, length, your P is load, and your A is area, your E is Young modulus. So talking about factor of safety is the next. Factor of safety, I wrote, it is impossible to accurately foresee the external loads to which a structure is subjected also at stress. So and this stress is below the elastic limit. The material does not retain any strain on unloading the member, but beyond this limit, a part of the strain usually remain after unloading the member. I come again. It is impossible to accurately foresee the external loads to which a structure is subjected also at stresses below the elastic limit. The material does not retain any strain on unloading the member, but beyond this limit, a part of the strain usually remain after unloading the member. Now, moreover, at times the available materials are victims of poor workmanship. So if you are to talk about factor of safety, you have to simply say that at times the available materials are victims of poor workmanship. So some of the poor workmanship tends to affect the limits of the material, that is the elastic limits of the material, and thereabout these factors too are taken care of by adopting working stress that is lower than the maximum stress. The maximum stress is also known as ultimate stress or yield stress, and is given as working stress is equals to this is your stress and over your factor of safety. Okay, do it to jot all this down. So this is an example. The question says a steel rod of 20 mm diameter and 500 centimeter long is subjected to an axial pull of 3000 kg. Determine 1. The intensity of stress. 2. The strain. 3. The elongation of the rod. Take E as 2.1 times 10 raised to the power 6 kg per centimeter square. So solution. From the question, the parameters include diameter is 20 mm. You convert to centimeter by dividing it by 10. So if I divide this by 10, I'm going to have it as 2.0. Add it into it to be meter, you divide it by 100. But this is per centimeter. And why I convert this, or this being converted to centimeter, is because the parameter of this Young modulus is given in kilogram per centimeter square. Okay. So from the question, you can find out that the length of rod is equal to 500 centimeter. That is the length here. And also the load is 3000 kilograms. So note from your Hooke's law, E is equal to stress over strain. Note that your stress is equal to load over area, not force. Your stress, I repeat, is equal to load over area, not force. Not force F. Okay. So the load is expressed in kilogram. Okay. So 3000 kilogram. Now Young modulus for steel from the question is given as 2.1 times 10 raised to the 6. Yeah, this is correct. You can do what you cram and retain that. While area is from the diameter, you note that you can calculate your formula for area as area is equals to pi r square, or you can substitute if you're for, let's say for diameter now, if you want to use this other formula, area is equals to pi r square, or your diameter is equals to radius is equals to diameter over 2. So therefore I can have my radius to do this, and I can substitute inside this guy, and I'll have it as area is equals to pi open brackets d over 2 all square. Okay, and I'm going to have my area is equals to pi d square over 4. So this is applicable for your diameter usage, or probably you want to use your radius, you make use of this. But it's very fast when it comes to theoretical question. Okay, so now back here, you're going to have your area as pi d square over 4. And from the question, you can find out that the diameter is 2.0 centimeter. And putting it there, you find out that your answer is, when you put your pi there, pi is 22 over 7, or 3.14. You have your 4, and you have over 4. This will cancel each other. You're going to have pi. So pi is 3.14 centimeters square. So you're going to have this answer. So the first question says that determine the intensity of stress. The intensity of stress is equivalent to the stress. Stress is load over area. So the load is 3000 kg over 3.14. Is the value, you get your answer expressed in kilogram per centimeter. Okay. So next question we have here is number 2, which is your strain. Your strain is equals to your strain. From the formula, you can remember that your Hooke's law, which is your Young modulus, is stress over strain, and from here you can find out that your stress, that is your strain. Your strain is equals to your stress over Young modulus, or your strain can also be equal to, if you remember, change in length over the original length. But here we only have this guy, and we have this guy, and we have this guy. So it's applicable. You can use your strain to now be your 95. As if I'm going to use stress over Young modulus, I'm going to have it as 955.41 over 2.1 times 10 raised to power 6. So I'm going to have my answer as, so I'm going to have an answer as 0.000455, or better, as you can see, 4.55 times 10 raised to power 123 for 10 raised to power minus 4. Your strain does not have any SI units, because it is length over the original length. That is change in length over original length, and then we cancel each other. So that is the answer. Now coming back to the third question. Third question says the elongation. You know, elongation is your change in length. Okay, so to find the change in length, you can come back to your formula that Young modulus, or simply you can come back to the formula of strain. Strain is equals to change in length over original length. Okay, Then from there you can get your change in length. That is, your change in length can now be equals to your strain times original length, or you can even use your Young modulus is equals to your load times length over area times change in length. So you can make use of this formula, apply them, or you can just simply make use of this formula. So making use of this formula is very fast and very simple, but we're gonna make use of this formula as well, so you can get along the textbook. Okay, so that will be 3000. Your length is what? 500 all over your area is 3.142. Your change in length, which from here, or rather rearranging this from here, you can adjust this and bring this here. So if I'll bring this guy here, that will be change in length equals to load times area times E, like this. So I cannot therefore to write this by saying that my E cannot be equals to, or rather my change in length cannot be equals to my that will be my P over L and my A over E. You remember, right? That is your original formula for Young modulus. So I'm going to have 3000 times 500, 3.142. My E will now be 2.1 times 10 raised to the power 6. So I can have my change in length as 0.2275 centimeter. Okay. Alright, so next question. So you can find out from here that we have our area as this, and we have our area gotten there. So the first one, stress. The stress is given as this. You have this answer, load over area. Young modulus is this. So you can find your strain from here, or you can also make use of this formula. But because we don't have this guy, change in length, so we can use this formula, and we have this. Multiply, have your answer. So using finding elongation, we make use of this. You can make use of this and test it is same, and also this as well, and you have your answer as this centimeter. Here is a second example. The question says a short hollow cast iron cylinder of wall thickness 2, that should not be 1, it should be 2 centimeter, is to carry a compressive load of 60 tons. Determine its outside diameter if the ultimate crushing stress for the material is 5,400 kg per centimeter square. Full stop. Use factor of safety of 6. So be considering the solution of this question. Okay. Alright. So here's solution. A short hollow hole diagram looks like this. So like you can see, this is the diagram of a hollow hole, short hollow hole iron cast, and from the diagram, these are 2 holes, and this is the outer diameter and this is the inner diameter. So let D naught be outer diameter and let D in be what? Inner. That is the inner diameter thereabout. So you can see that the thickness of the wall, this is inner diameter, sorry. The thickness of the wall is 2, and this will be 1, 1. So from the question, you can find out that the question originally was 1 meter. So for both sides, if you add the both sides together, you find that it's 2 meters. So this is your diameter inner, this is the diameter outside, and this is the 1 centimeter for both sides. So that is wall thickness. So we can say the wall thickness is now 1 plus 1, that will be 2.0 centimeter. So from here you can find out that the outer diameter D naught will now be equal to what? Inner diameter plus 2. Can you see? That is this outer diameter will now be D inner plus 1 plus 1, right? So you can say plus 1 plus 1, that will be equal to D in plus 2. Okay. So from there you can find out that also that the ultimate crushing stress, you can find out the ultimate crushing stress is equal to, you find that is P over A. also the working stress. And you can find out that the safe load is equal to the crushing stress over the crushing load over safety factor. That is this load over safety factor. So by default, you can also say that the total area is also equal to the area, outside area minus the inside area. That will give you the area difference. That is the total area. So you can also say area of outside diameter d naught. That is area of outside diameter. Area of outside diameter d naught. Of outside diameter d naught will now be equals to A. That will be equal to A naught. A out is from your normal standard formula of area. You remember area is equals to pi d square over 4. I've just proved that now. So from there you can now substitute that. That will be pi d out, that is square, over what? That is over 4. And this is the one that has a square. Okay, that is for out. And also for in, you remember that for in as well will now be A in. That will be A in equals to what? Pi d in, right? Pi d in square over 4. Okay, so also remember from the formula that your d out is equals to d in plus 2. So therefore you can also find out that your d in is now equal to d out minus 2. Okay, so from here then we can substitute this d in inside this formula here. So I'm gonna have area in inside diameter or inside will now be equals to pi, and I'm gonna put this guy inside, so I have it as pi d naught minus 2 all square all over 4. If I decide to expand this guy, I can also have it as pi over 4, open the bracket, d naught minus 2 all square like this, and say all over 1 if you want, thereby like this. So therefore also I can now do it to advance a bit by saying my area in will now be equal to my pi over 4 open bracket. So if I open the bracket of this man, let's open the bracket of this. I'm gonna have it as d naught minus 2 and d naught minus 2, right? You remember, just simple factorization, and I'm gonna have it as equal to pi over 4, and that will be equals to open brackets d naught square. You remember, that is d naught square, and plus this times this times this 1, this times this, so that will be minus 2 d, that is this times minus 2 d naught, this times also minus 2 d naught, and this will be plus 4. So I'm going to have it as equals to as well as pi all over 4 open bracket d square minus 4 d naught plus 4. Okay, so or I can also decide to rearrange this pattern and make it equal to, by substitute minus out, I bring minus out, I'm going to have it as pi, that is minus pi over 4 open bracket. I will have here as what? This will be minus d square, you remember, plus 4d naught minus 4. So this concept I just did now is I decided to bring minus out. So if I multiply through by minus, I'm going to have minus here, and that'll be minus, that'll be minus d naught plus minus. So that'll be minus times minus will give me plus, this minus times plus will give me minus, minus times minus will give me. So I just rearrange this, and Also, I can also move and saying if I split it, I'm gonna have it as equals to. So let's keep this minus. Let's keep this minus separate. So I'm gonna have it as pi over 4, and I'm gonna have it as this pi over 4. If I multiply through, I'm gonna have it as pi d square not over 4 plus. If I multiply through, but I also have it as 4. That is pi. But I can open the bracket and collect them as pi over 4 open bracket 4 d naught minus 4, like something like this. It's still the same thing. Okay, so I just decided to bring, instead of splitting it there. And also I can bring 4 outside. So if I bring my 4 outside, I'm gonna have it as my minus. That I'm gonna have it as minus. This minus is here, so I need to multiply this by. So I'm gonna have it as minus. Don't forget that this minus is still there, separate. So minus pi d square not over 4 plus, I can bring 4 out, 4 pi all of d square not minus 1 all over 4. Cancel, you get. Then I'm gonna have my answer as pi d square not, pi d naught square rather, plus pi open brackets. You see my 4 had cancel each other. I'm gonna have it as pi this pi open bracket d naught minus 1 and all over. It has cancelled each other, so 4 is gone already, and I'm gonna have it as this. So this is also our area in. And don't forget that our formula originally says that d out is equals to d in plus 2, and d in is equals to d out minus 2. Okay, so we're trying to bring this from this concept here. Okay, and we also know that AT is equals to our A naught minus A in. Okay, minus A inside. Okay, so if we talk about area of X section, so the area of X section, that is, if you section that diagram like this, I have the length. If I section it like this, if you see this outer part, it will be something like this. You can also see this inward part. You see the inward part of this half cross section. You see the inward part like this. So if I'm to find the area of X section is also your AT, I said it, and it's equals to your A out minus A in. So this concept here, don't forget that from the formula that there is negative sign, this negative sign. So this negative sign is still also here down to here, so it's still like this. Okay, so it's still like this. So this negative sign outward, don't forget there's also negative sign inward here. That is from this guy. I come again, when you solve, you find this negative, that is by reverting it here. That is negative sign here. This one you multiply, you still have the negative sign here and this. So this negative sign is still here, and it's still here, and it's still here, thereabout. So this negative sign now can be brought to this side. So if I bring this negative sign, here to this side, I'm gonna have it as minus A in equal to minus pi d square over 4 plus pi open bracket d naught minus 1. Okay, so if I bring this concept here like this, I cannot translate it to now be AT equals to, so my A cross section, AT or AX, either way. So let me use AX as A cross section. The area of the X section cannot be equal to my A out minus A in. And if I bring this guy, I can have it as A out, and I can have it as this is also this. So I can have it as minus all this concept. So I can also say plus A in. It will still give me the same answer. So I just want to write this here. So I can have it as AX equals to my A out, and my A out already, remember, is pi. I've already solved that before. Pi d square all over 4. then that will now be B plus, because this should give me minus, don't forget, but because I already have minus A in as this, so it will now be plus. Okay, so you can have it as plus, open brackets, my minus pi d naught square over 4 plus pi open bracket d naught minus 1. Okay, like this. So this concept here, that is, let's say over 1, this concept here can now lead us to have AX equal to, if I open my bracket, I'm gonna have pi d naught square over 4 minus pi d square d naught square over 4, and if I open the bracket, I will see have plus, that is, I'm opening the bracket, I will see have plus pi d naught minus 1, like this. Okay, if I decide to put over 1, then I still have my same answer, like this. So therefore I can have my final answer to now be AX, to now be A cross section will now be equal to this guy, we cancel each other. Okay, so I'm going to be left with pi d naught minus 1 centimeter. Okay, that's pi d naught minus 1 centimeters. So I explain again. Starting from the formula, you get to arrive at here. So when we find out that A in is this, I rearrange this by multiplying through by negative. So when I multiply through by negative, I'm going to have minus out. This sign will change to be minus, this will be plus, this will be minus. Okay, so this negative sign is here. Then next thing we do is we collect and bring out. I multiply this by through all this. So I have pi over 4 times this, that will be minus pi over 4 d square. Don't forget that this minus is still here. Okay, this minus, sorry, so this minus is still here, and this minus is here as well. So multiply this by this, I'm gonna have this, multiply this by this, I'm gonna have this, and instead of multiplying this through, I just decide to bring pi over 4 open bracket 4d naught minus 4, and here as well, minus is the minus, this minus is still here, and this minus is still here. That'll be pi over 4 d square plus pi over 4, and this is opening bracket, collecting the like terms, rather collecting 4 out, so I have it as 4 we leave, and I have it as 4 pi over d naught minus 1 over 4. This will cancel each other, so I'm gonna have this minus here is still here, and this minus is still here, and this minus is still here, and also this is pi d square over 4, like plus this has cancelled already. I have that pi d naught minus 1. Then remember that the area of a cross section total will give you your area of the outward, that is the outside minus area of the inward. So we can now remember that our d outside is also d in plus 2. D in can now be, if I bring this guy to here, d in equals to d out minus 2. So therefore area of x section of that particular whole cast as before is this. So do you remember that this A in is minus this. So if I multiply through by this guy, I will still have an answer. But I decided to bring this minus to this side, so I can have it as minus A in equals to minus pi d square over 4 plus pi, like this. That is, if this minus comes to this side, I'm going to have it as minus A. I will have it as minus A in equal to minus this. So I have this concept. Then put it inside using this. So in getting here, our AX, our AX originally is AT equals to, or let's say AX equals to A out minus A in. Okay, but because we've gotten A minus AN as this, so I can just represent it by plus A in. So you see, give me the same thing. Okay, so and I have this, and I put it here. That is our A in outside is also by this over 4, and my A in, that is my minus A in, is also equal to all of this, and I write it here. Open your brackets, do this, and you have your answer as the centimeter square. Okay, So for ultimate crushing stress, you can remember that ultimate crushing stress original formula is that the crushing load over the area and the length, but your length here is 1 centimeter. It's just default. So your stress can now be equals to this is the this man is the ultimate crushing stress, is now your load over area. Then this ultimate crushing stress here can now be, if I cross multiply, I'm gonna have my load, that is my crushing load from here. At least I will have my P because to my stress times area. Okay, so and you have it as this, that is your stress multiplied by your area. So okay, and if I cross multiply, so I can have my ultimate crushing stress here. If you remember that the formula we derived, and that is I will have it as this times the area, and I can have it as the 5,400 kilogram per centimeter square. If you remember from the question, the parameter we are given this, and it's kilogram per centimeter square, and your area of the cross section is now derived as this. So this was one of the ones that take a bit time. So you can have your load as this. Then we can now move forward that okay, we can have our load as this formula, as this answer. And then remember that my centimeter here, we cancel my centimeter here for the area. You can have this and I can have this as the crushing load. So for compressive load or safe load is when it's shortened. You can have it as equal to your crushing load over safety factor. That is your P over your safety factor. And you are given safety factor from the question you find out. So working stress is originally your ultimate crushing stress over the safety factor. So the working stress is your ultimate crushing stress over safety factor, and you find out that we are given the compressive load. The compressive load is given as 60 tons. So compressive load is equal to 60 tons. And if you find out from the standard that 1 ton is equal to 1,000 kilogram. So you can find out also that 5,400 kg can also be equal to 5.4 ton. Okay, it's 5.4 tons rather. And you can now see that from this working stress formula, that the working stress, we are given the compressive load that is as 60 tons. So that can give us that can give us 60 tons will now be equals to the stress. You remember we've solved that particular load, that is our P, our stress, this crushing stress. We've solved it as 5,400 pi open bracket d naught minus 1 kilogram. That is the load. And the safety factor we are given a safety factor of 6. So therefore we can now find our outside diameter, and we can find out that if I cross multiply here, I'm going to have my d naught, because I will have this, my d naught will now be given as, or to simplify it, I can have it as this, that I will have it as 3,360 tons equals to 5,400 pi d naught minus 1 kg, right? Then to get my d naught, I can now say that the d naught, that is, I can divide both sides by 5,400 pi, so you can have it as d naught minus 1 equals to 360 tons over 5,400 pi. And you remember that this is in kg. So if I want to convert it to ton, remember it is equal to 5.4 tons. So that will now be d naught minus 1 equals to 360 tons all over 5.4 pi tons. Then you can cancel each other, and I can have my answer as therefore from there. But don't forget that we can have my D naught now be equals to minus 1 will now give me this 360 over 5.4 pi. Then I can now have my D naught now because of 360 over 5.4 pi plus 1, and I can have D naught is now equals to 22.22 centimeter. Final answer. Okay, it's worth it. Okay, so also I explained that from here you can have your working stress as this, your 1 ton is this. From there we can put the formula, that is the compressive load or safe load is equal to this your that is your P. Remember, your P is your crushing load, so it can also, because your crushing load over safety factor, if you remember the formula like that. And also we can do it to, that is, you can apply this, or you can simply say this in case if it's confusing. You have that, and that will be this. So I put this guy here. You just got this the previous time, and put the safety factor we are given, and it's 6, and I cross multiply 3600 5400 pi. From there I divide both sides by 5400 pi, 5400 pi. So to convert it to tons, I have this kg is in tons, then cancel and make my disobey formula, and I have the final answer as 22.2 centimeter. Okay, yeah, this is elongation of bars of varying cross sections, and from diagram here you can see this is a box, this is a particular block that is hinged to a wall. If I turn this side like this direction is cantilever, that is, it is hinged to the wall. So you see it eventually has support downward like this. But if this is turned back to the appropriate place like this, yeah, you see the axial pull will be downward. From here it will be dragging it down, the gravitational force. So you remember from Hooke's law that E, that is your Young modulus, is equals to stress over strain. Stress over strain. And you know this can also be, stress can also be load over area divided by, this is your change in length over original length. Okay, so and you can eventually have your E to now be PL over A times change in length, and therefore we can now say or this can come here. I'll have it as my change in length can now be equal to PL over AE. So this is a standard formula for calculating our change in length. Now applying it to each distribution of this length of this load, this is axial pull. So we can now say that for L1 I will now have the change in length L1. So I will now have it as change in length for L1 will now be equal to my P L1 over area 1E. Also for L2 I will still have it as change in length 2 will now be P L2 all over A2E. Remember that Young modulus is constant. So same thing for my 3, I will have it as L3 equals to P L3 all over A3E, and so on and so forth, like that. So now combining the total length together, because they are acting alongside each other, so we can now have our total formula as, so total change in length will now be the total change in length. Change in length will be given as the addition of this L1, L2, L3, and that will be change in L1, L2, L3. And if I add it together, I can have my change in L1. If you remember, that will be P L1 all over A1. So I'm going to have it like this thereabout. So I'm going to have the formula. So from here, we complete it. Then if I collect like terms of my load and my Young modulus together, I'm going to have something like this. Collecting this, so I have L1 over A1. So this is the bar the elongation formula of bar of various cross section. So we'll be looking at an example and we'll move. So considering this example, the question says a bar 30 centimeter long is 5 centimeter square in section for 12 centimeter of its length, 2.5 centimeter diameter for 8 centimeter and 4 centimeter diameter remain length. If a tensile for a 10 tons is applied to the bar, calculate the maximum and minimum stress produced in it and the total elongation. Assume uniform distribution for load over the cross section. Take E equals to 2 times 10 raised by 3 tons per centimeter square. So as you can see from the question, so we want to draw the diagram. Question says a bar 30 centimeter long is 5 centimeter square in section. So it is 30 centimeter long. That is the total length of the bar is 30 centimeter long. So that means we have the total length to be 30 centimeter long. And it's a square one. So a square bar. Then the question says next that for 12 centimeter of its length, 2.5 centimeter diameter for 8 centimeter. So we have 12 centimeter for its length first. So we have, let's say, the first part from here to here is 12 centimeter. So that means that we have this Mr. Man here, 12 centimeter. Let's say bar 1. And we have the diameter to be for 12 centimeter was for 12 centimeter its length. So it's 5 square in section 12 for 12 centimeter. So we have the 5 centimeter square here for the diameter of 12 centimeter. Next question says 2.5 centimeter for 8 diameter for 8 centimeter. So next one is 2.5 centimeter is half of this, so it will be like this. Then we can have this half here. So this is not gonna be here, and we say just 8. That will be very short, and like this. It's not gonna be here because they said 8 centimeter. So we have this length here to be 8 centimeter, and diameter is 2.5 centimeter. So next one says and 4 centimeter diameter remaining of its length. So from the 30, the total is 30. Don't forget that will be 30 centimeter minus 12 minus 8, that is 20. That will be remaining 10 centimeter. So here, from here to here will be 10 centimeter. So, and we are told that the diameter of this particular 10 centimeter here is 4 centimeter. So obviously it won't be up to this 5 centimeter. It won't be up to this 5 centimeter. It will just be a bit low. This is just a sketch, and that will be 4 centimeter diameter. So we've done justice by drawing the diagram first. Next thing is now to solve. If you remember, the question says we are given parameters and we are told to find the maximum stress and minimum stress. So that is part 1. The first thing we'll do is that we have the total area. First area is 5 centimeter. So therefore the area 1, for the area 1, for this particular guy 1, we are given diameter as 5 centimeter, right? So you can have the area as what? Length times breadth. So for this area, since it is 5 square in meter, we can have our area to be length square. Not this length, but the diameter here. Okay, the diameter simply represents this length. So you can have it as L square, that will be 5 square, and that will be 25 centimeter square. And we have our original length. So this is just the diameter for the length, then our original length. So you can see this is also for the diameter. Then for original length is for this guy, the original length is 12 centimeter. This one also we have 2.5. Okay, so for this 2.5, you can see now this, the first one we have the question to be 5 centimeter square in section. So for 12, we have this 5 centimeter square in section. So we are given 5 centimeter square already as the area of this. But for the second block, we are given as 2.5 centimeter diameter. So for A2, we are going to make use of pi d square over 4 because we have the diameter as 2.5. So that will now be pi, that's 20 over 4, 20 over 7 or 3.142 times the d is 2.5, that will be 2.5 all square over 4. We can have our answer as 4.91 centimeter square. So for the third question, we are given and force of 4 centimeter diameter. So as well, we're going to make use of pi d square over 4 for A3. Don't forget the length for this L2. L2 will be equals to, we have it as what? 8. So we can have also that for A3, we can have it as pi d square over 4. And that will be pi times our d here is 4. That will be 4 square over 4. And that will still give us 12.57 centimeter square. And the L3, don't forget the L3 is also equal to what? 10 centimeter. So therefore, you can find out that for axial load and stress and strain, the smallest stress will always occur at the largest length. The longest length, we have the smallest stress. So by default, this will give us the smallest stress because it has the longest length, and this will give us the biggest stress. So but let's show it first. From the formula, remember that formula for your stress is equals to load over area. So for maximum stress, that will be the P max, that is your load over the area max. And you can see for sure that the one that has the load we are given from the question is we are given 10 tons, and the maximum area occur at what? That is when you have it as 4.91, because the maximum area, that is the greatest the value that we have from the lowest value of the length. So we have the lowest length to be 8 centimeter, and the maximum area will occur when we have our answer as 25. Okay, but for minimum now, so let's start for minimum, or for maximum rather, that'll be 25. So we can have it as 10 and our 5 here. I come again. Your maximum stress will always occur at the lowest length, 8. So you can determine it by default, but for value purpose, your stress is equals to load over area. So your maximum area is when you have your value of your area to be the greatest, and which is 25. The first one, A1, we have is 25. Second one we have is 4.91. Third one we have is 12.57. So you can see that this one occur at this guy here, which is your 25 maximum. So I put the maximum here, and that is 10 over 25, and we have an answer as 0.4 tons per centimeter square, So now find our minimum. Also, we can have it as our minimum stress will now be P over A min, and that will be equal to your 10. The minimum area will also occur at 4.91, and our value can also be equal to 2.04 tons per centimeter square. So you can see that by default, this has the largest value, and these are the longest, the lowest value. But this is the maximum and this is the minimum. So we've solved the question. Okay, now if you are to find the total elongation of the question, total elongation from the formula, remember that is a change in L cannot be equal to your what? P over E into bracket your L1 over A1 plus L2 over A2 plus L3 over A3. So that is your to find your elongation, the total elongation. You already proved the formula before, so you just plug the parameter inside. What is your L1? 12. Your A1 is 25. Your L2, put it there, and you find your load. You have your elongation, your Young modulus as well. So we have it as this. So you can see like that, and now we can just put the value there. So our P, don't forget, was 10, and we're given the value of the Young modulus as 2 times 10 is 3 tons per centimeter square. So, and we have our L1. Our L1 is 12. Our A1 is 25. Our L2 is 8. Our A2 is 4.91. Our L3 is 10. Our A3 is 12.57. So like I said earlier, that you have this, and you're gonna have the answer as 0.01453. So from here you can find out that the biggest stress will always occur at the biggest stress will always occur at the minimum strain, minimum length, and you have the lowest stress at the value of your longest length, and you can have your change in length like this. Okay, so now we're talking about Poisson ratio. So like I said earlier, that your Hooke's law, remember, you have your constant as Z, and that is equals to your stress over strain. So Poisson ratio here can be defined as the ratio of the lateral strain to the axial strain. So bringing it into practical application is, imagine when a load is subjected to a force or under a force, example your ceiling fan in your room, or your bulb, or let's say you hang your glass, your mirror, or a typical example is you hanging your clothes in your room. So when you hang it, the cloth is a load and subjected down. So this cloth is in this form. Let us give it a typical example. And you see the axial pull will be toward the gravitational force. That is the gravitational, where the earth core lies, and you should pull it down. So now your Poisson ratio is when you drag this. Now imagine you want to pull off your clothes from this hanger. So when you drag the cloth up, you tend to pull, so you apply a force. By default, this hanger will somehow compress a bit. So it's either it reduces like this, the length should reduce somehow like this, somehow, and in order for it to come off this edge, then once it is off this, it comes back to its original state, and that is elasticity. You remember the drain rim like this, and it breaks off. So same thing is applicable to this. So in a nutshell, this lateral strain, that is this particular line, this particular side line here, tends to somehow compress a bit, while the other side here expands, and you know this elongation. So this is the lateral strain to the axial strain, and for most metal, they range from here to here. So let's see some example, consider some example. So considering this example, don't forget this is your Poisson ratio, and this is the lateral strain to axial strain. So considering this example, a scale steel bar, like just a scale steel bar like this, 50 millimeter on a side, like on a side. Look at that statement, on a side. So one side, a scale is not, this is not a scale, sorry, a scale is like this, has both lengths to be equal, and as a side, a single side, 50 millimeter, thereabout, and 1 meter long, is subject to an axial tensile force of 250 kilonewton, determining the decrease in lateral dimension. So decrease in lateral dimension talks about lateral strain due to this load. Take your Young modulus to be equal 200 giganewton per meter square. You know 1 Pascal is equals to 101235 Newton per meter, or simply 1 Pascal represented as 1 P equals to 1 Newton meter per square. So using this giga is 10 raised to power 9, y pico is 10 raised to power minus 12, femto 10 raised to power minus 15, you have your z2, I already explained that, 10 raised to power minus 26. Okay, so we have 1 gigapascal or 1 giganewton per meter square to be with this value of your Young modulus, and you have your mu. This is mu and is your Poisson ratio to do this. So solution, looking at this example, is very simple. Just apply. First thing is you want to get this lateral strain, you need to get the axial strain. Okay, and you know your axial strain is your, you can get it from your stress. Stress is equals to that is the stress equals to load over area. And what is your load in this context? You find out that you need to get your area. Your load here is what? Or tensile force 250 kilonewton, right? So you have your 250 kilonewton and you have your area. So from here you can find out that you have the skirt still to be 50 millimeter. So suspense. If you're writing this, I want to suspend you. If you write this, just for a few minutes, solve this, okay? So if truly you solve it, you find out that you're very careful with this value. You see, you tend to make small mistake with this value because your formula for area is pi d square over 4. But in this context, look at the situation and say a skirt T bar 50 millimeter on a side. So I can apply my formula for length times breadth, or you say L square. So my L in this statement is 50 millimeter. That is 50 times 10 to the minus 3. And if I scale this, I'm going to have it as 2,500 times 10 to the minus 6. Okay, so and if you solve this, you're going to have your stress as this. So now solving your strain is equals to your from the formula, Young modulus is equals to your stress over strain, and I can get my strain to now be my stress over Young modulus. So I've gotten my stress and I have my Young modulus to be given as 200 gigapascal or giganewton per meter squared. So you have something like this. So applying the parameters, appropriate parameters into your stress Young modulus, you can have it like this. Then your stress will now be 100 times 10 per 6, that is for the megapascal, 200 times 10 per 9. This 10 per 6 is gotten from the value of the stress, previous answer, and your strain does not have any dimension, it's dimensionless. So I can solve for the Poisson ratio now and say Poisson ratio is my lateral strain over my axial strain. Don't mind writing since you know the formula. So now to get my axial strain will now be equal to what? My mu will come here, so I'm gonna have it as the lateral strain over my Poisson ratio. I can have my axial, let's say we want to write our axial strain like this, equal to, or appropriately you can write your axial strain. So since it is strain, you can just put this not shorten like this, full stop. That is applicable in engineering terms. Your lateral strain, you've forgotten, you got the value ahead before, that is your 5 times 10 to the minus 4. Another thing is that the word lateral strain literally means a load subjected to an axial pull that has this pull P and is acting alongside. The word here is very important. So this side is your strain. So the lateral strain, you can see it's this side, the elongation part for this side. So if I'm going to solve this now, I'll just put the lateral strain. So in a context here, if I'll find this lateral strain now, you know, my axial strain will now be equal to my lateral strain over Poisson ratio. But in this context, my lateral strain is what I'm looking for. So my axial strain is this. I come again. The axial strain is that which tends to act like this. Okay, the axial part, and my axial strain. So I say we should shorten it like this, and I can have my axial strain, that is this guy here, to now be equal to. My lateral strain for the lateral strain will now be equal to my Poisson ratio times axial strain. Okay, so from this context I can have my lateral strain so now because my mu is 0. We're given as 0.3. So 0.3 times 5 times 10 to the minus 4. I can have my final answer as 1.5 times 10 to the minus 4. Correct. But does not have any dimension, is dimensionless. Okay, so but most times you can tend to put your answer, since this distance, you can put in radians. That is for different places if necessity or coordinate is very important. So therefore you can have your answer as that. Okay, so finally, for converting to a 50-meter length, for a 50-meter length, that is like the question now, for the scale 50-meter length, you need to multiply it by that length. That will be 50 millimeter times 1.5 times 10 to the power minus 4, and you can have your final answer to now be 7.5 times 10 to the power minus 3 millimeter. Write this extra chapter, write this as. Okay, write all the notes alongside. So the next we have here is compound bar. If you just take some few minutes now, the preliminary, I just depict a preliminary statement there that talks about compound bars. So this compound bar is any tensile or compressive member which consists of two or more bars or tubes in parallel. Example, now this is a bar in parallel. You can put more, I can add more to this. So these are compound bar. Any tensile compressive member which consists of two or more bars or tube in parallel, usually of different materials. Different material in context mean this can be steel, this can be copper, this can be strontium, this can be yttrium, deuterium, or selenium. Typical example we have here, this can be your iron here, and we can put different materials there. We can have gold thereabouts. So they can be of different, but they are majorly of different materials. So you can have the tensile stress, you can have compressive stress for this, you can have this what give birth to bending moment, whereby assuming I press this guy together like this, I'm gonna have it will bend like somehow like this. Unlike the way it is like this, the diagram will simply just be something like this. So look forward to the bending moment part, very important. Okay, so any tensile or compressive bar or tubes in parallel arranged, which comprise two or more bars in quotes arranged in parallel of different different properties or different materials. Simply the arrangement of different bars made up of different parameters or different material arranged in parallel. These are called compound bars. It can be 2, it can be 3, it can be 4, thereabouts. Okay, so now talking about shear stress and shear strain. Unlike your normal stress is stress is equal to your the load over area, while your strain is equal to the change in length over the original length. Okay, but in this context here, so the shear stress and shear strain, unlike your normal stress and strain, the word shear there means there is a different force that is uniform to the previous one, but tends to have greater force, greater weight, or it tends to drag it alongside. See, for example, this particular cylinder, due to this shear stress that has shear force, because shear stress is equal to shear force over area. It's very important you pay attention to the detail. Okay, it's very necessary, it's very important. So this shear stress here acts along as acting perpendicular to the cylinder, and at the center along this horizontal portion like this, you will have the normal stress. Okay, so this normal stress P is acting along the cylinder, that is horizontal direction, and this shear stress is always acting perpendicular to the body or to the member, be it compressive or tensile. Okay, so you have the formula like this. You have the same parameter, the SI units, you have your Newton, you have your meter square, and you can still be Newton per meter square or Pascal. Like remember 1 Pascal it's also 1 atmospheric pressure, rather 1 atm is equals to 101235 Newton per meter square. Okay, so yeah, some textbook based on some textbook make use of rigidity as the modulus of elasticity for shear. So this is the modulus. Unlike the Young modulus, which was denoted as E, this is the modulus of elasticity in shear. So we now have this modulus of, we can call it modulus of rigidity. Modulus of rigidity or shear modulus. Why this is your Why is your shear strain? Shear strain. Remember, elasticity modulus, Young modulus also stress over strain. So shear stress over shear strain. So when you have a question, an example, let's say something like this, a bar like this with this particular, let's say in terms of a chisel that is half bridge, and you have this particular joints there as well. And if I pull this man here to my right hand side like this, what will happen? This guy will tend to expand. So this joint will cause this. So by default, you have rigidity, and this phenomenon is called shear modulus. Okay, and you can find the differences. If you are given a diameter, let's say diameter you are given is 10 let me say 10 millimeter. You can find the area. The area is equals to pi d square over 4. Okay, so then you can substitute this inside, you have your answer. And in different cases, you can have, if it were to be half of it, if you want to find this half, you can define it, but not really important. So the main important thing is that the summary of everything, that your shear stress cannot be equal to formula for the stress originally is load over area. So you can have this as Fs over area. So in case you are given a question you want to solve, you have let's consider this example. So this example, the force P of a boat is 30 kilonewton and diameter of the boat is 10 millimeter. So imagine you want to draw it often. You have a boat. Let me say this typical example of a boat can be like this. Something like this, having this. So this is a boat here, but this boat has belt. So the force of a boat is 30 newton. So the force P of a boat, so let's say it's dragged or it's hinged. So let's say a force is acting on top. P is 30 kilonewton and the diameter of the boat is 10 millimeter. So the diameter we're given here is 10 millimeter. Diameter is equal to 10 millimeter. Say determine the average value of the shear stress. So the average value is just the half of the shear stress, and you remember that your shear stress is given as this, right? So that is, they say you should find the half. You are told to find the half of this guy. So thereabout, you can remember that your formula for this is this equals to your shear stress equals to force over area. So you are given the force as 30 newton, 30 kilonewton, that is 30 times 10 raised to power 3 newton all over your area. From the question is you make use of pi d square over 4. So that is pi. What is your d? Your d is 10 millimeter. You can decide to convert to meter, or let's say you convert to meter, that will be 10 times 10 raised to power minus 3 over 4. You find your answer, you solve that. So now let's say on a case like in a case whereby you have it as 10 meter, you simply have your diameter to just be simply 10, okay, and that will be pi d square over 4, and I can solve then I'll have my top. So now to find the half value of this shear stress, that will be divided by 2. I can have my answer as, that is half of P of A. I can have my final answer as 192 megapascal. Yeah, the mega is 10 raised to power 6. Okay, so 192 megapascal. Put your value there for, then you have your answer as this, depending on the choice you want. So that is that about that. Now we'll be considering the second chapter, the third chapter, which talks about shear force and bending. So we'll be considering shear force, considering the next topic, which is shear force and bending moment. So we do it. So subscribe, and so I'll privately unlist it for you guys, okay? And assignments are very, very important.